So in this lecture, I'm going to go over thermal boundary and heat transmission. So we'll go over some of these basic concepts such as um, the building envelope, conditioned space versus unconditioned space, and then we'll discuss how heat is transmitted through a surface. Go over the real basics of insulation. We'll look at the concept of heating degree days, and then finally we end on how to calculate heat loss through a surface. Okay. So the building envelope, as you can see here, is the area of building that encloses the conditioned space. Otherwise, it separates the conditioned space from the unconditioned space. Okay, so conditioned from unconditioned. Conditioned space is the area of the building that you actively heat and cool. And so in this image here, we have what looks like it must be a finished basement, a first floor, a second floor, and then a porch that is also heated and cooled, or a room here, maybe a sunroom, who knows. And so you can see here the insulation is indicated here. The building envelope, unless the insulation is missing, it will you can find where it is because it's where the insulation is. So hopefully that should sound familiar because that is also our thermal boundary. Some people call it thermal envelope, but it's really coincident with the thermal boundary. And so anything in here it must be actively heated and cooled, right? So there must be a finished basement where they're heating and cooling that as well. You can see the little arrows here. If a lot of folks have unconditioned basements, so you can put the envelope here, and then this would be unconditioned space, and this would be conditioned space. So that's really important. And in terms of the heat flow through the building envelope or through the thermal envelope, it's based on the second law of thermodynamics. Okay, so we've gone over the first law, which is energy cannot be created or destroyed. The second law is that the entropy of the universe always increases, which, in other words, the sort of chaos of things around you increases through time. Entropy is a measure of disorder. So higher entropy means more disorder, and you're less able to do work with that thing. So when we're talking about energy, the higher entropy energy is the stuff that you just can't do as much work with. And as it turns out, the high entropy energy, um, the highest entropy, heat has the highest entropy, excuse me. So what does this mean for our purposes? I'm not super concerned. You know what entropy is. What I need you to know is really two things. Um, Number one, that 100% of the energy cannot be transformed into work. In other words, if you convert energy from one form to another, or if you use energy to do something, which implies that you're converting it, um, it can never be 100% efficient. Okay, so you always have some loss. So if you look at a furnace or a boiler or whatever, it's always going to be less than 100% efficient. That's why I say a heat pump, the rating on that is technically not efficiency because you can get more heat out than energy you put in, but that's because you are not converting the electric energy to heat. Remember, that's your refrigeration cycle. Anyway, when you convert energy from one form to another, 100% of it cannot be used to do work. The second thing is that heat always travels from warmer to colder areas unless energy is added. So for our purposes, heat will always travel from warmer to colder areas. Okay, so those are the two implications of the second law. And so in terms of the heat flow, that is really important because heat is going to flow from the warmer areas to the colder areas, and it's going to happen. So all you can do is limit that heat transfer. And so that's why we use insulation, because it helps limit that heat transfer. And insulation, helps prevent heat flow. It has what's called a higher R value, which we'll go over in a minute, or a lower U value. But an important phenomenon that happens in buildings, this is both in residential and commercial buildings, is you have something called thermal bridging. So you want to jot down thermal bridging. And a thermal bridging is when a building component conducts heat more readily than another building component next to it. A good example of this is if you've ever had a fire safety training or class, or even in like elementary school, probably some kind of fire safety. They always say to if you want to see if there's a fire on the other, like you're in one room and there's a shut door, You're like, I'm not sure if there's a fire in the other room. You can touch the doorknob and see if it's hot. Second, another thing is like just don't grab a doorknob if you think there might be a fire on the other side. So if you touch it and it's hot, that's an indication that it's really hot on the other side. And why is that? Because the doorknob is made of metal, which really readily conducts heat, whereas the door is not made, well, maybe it's made of metal, but um, if it's made of metal, there's probably a foam core or some kind of insulation. Um, and so the doorknob is a thermal bridge because it conducts heat really well relative to the other components. Um, although that's sort of the opposite way to think of that is on a really, really cold day outside, if you ever touch the doorknob and you're inside and it's really cold, that's because heat is conducting through the doorknob going out, and that's causing it to be cold. But a really important implication of thermal bridging and is very common in buildings. If you look at this image, this is an actual infrared image, so it's detecting heat, and it's from outside of a building on a really cold day. You can see we're in centigrade here. So you can see this dark pinkish purple areas, and then these brighter yellow areas. So if you look at the temperature scale, the brighter yellow areas are -8, so they're cold, but we're looking outside. Must be a really cold day. But these darker areas are like -15, right? So they're even colder. So these stripes, these orange, yellowish orange stripes, are relatively warm compared to the other areas. And why is that? Well, it should look familiar, right? Like this is obviously framing. So these are your wall studs, and this is your top plate. You see a bottom plate here. I mean, it's crazy. You can see the actual components. That's because wood is a bad insulator, and so they're thermal bridges. And the warmth is coming from the heat inside, right? So remember, we're looking outside, and so those areas are warmer than these, which are insulation. And the windows, you can just see heat because glass is a terrible insulator, even worse than wood, and so they're going to be warm from the outside. Okay, so that's thermal bridging, very important phenomenon. So looking at how do we know how much heat's going to flow through a surface, we need to know U value. U value. This is what we really need. R value is helpful, but the only way we use it to calculate heat loss is to convert it to U value. And I'll show you how to do that. It's really easy. So U value is how much heat, BTUs, flows through a 1 square foot slab of material every hour when there's a 1 degree temperature difference on either side. The unit implies that BTU per square foot per degree Fahrenheit per hour. So it's a measure of how readily it transmits, right? So remember, this is how many BTUs flow through the surface. So a higher U means more BTUs flowing through. Therefore, it's a worse insulator. All right, so let's look at a few examples just to sort of hammer this home after we go over R value. Sorry. So R value it just tells you how good of an insulator it is. It's the inverse of U value. Okay, so it's inverse, so it's 1 over U. So if you think about it, remember, a lower U is better because it's less transmittance. But R is 1 over U, right? So if you drop the U and you divide 1 by that, you can do some sample calculations on a calculator if you want, and watch how the U goes down, the R goes up, right? Because you're dividing 1 by it. Yeah. And so higher R is better. Now this is nice. It's convenient because it's very intuitive. We usually think that bigger is better, right? So a higher R is better insulator, right? So an R38 is twice the insulating value of an R19, and so on. So it's proportional. Um, and so we know that you stack R's on top of each other, you're going to get more R. And we'll talk about that. You can add R's together. Um, yeah, so higher R is better, lower U is better. So everything has an R value, everything has a U value. Every building component, window, sheathing, framing, insulation, it all has an R value and U value. So really nice thing about R values, another nice thing, you want to jot this down, is that R values can be added. U values cannot be added. I mean, you can add U values if you want, but it's not going to give you the right answer. All right. So remember, U value is how much heat is flowing through a 1 square foot surface when there's a 1 degree temperature difference over the course of 1 hour. Lower U is better because it's transmittance. Higher R is better, and R is the inverse of U. Remember, you can add R's, you cannot add U's. Very important. And R's are great because they're very intuitive. You take R11 and you lay it on top of R38, you get R49, right? So it's nice and easy. Um, and so that's why R's are convenient. And then you can then flip that and get a U value. So how does how does it all work? I mean, this is an important principle to understand. It's that insulation and good insulating materials, um, they help prevent heat flow through conduction, convection, radiation. This is a pretty good example or illustration of how that happens. Okay, so this is an electron microscope view of fiberglass insulation. So this is just these extruded glass fibers, right? So that's what fiberglass is made of. So just imagine it's warm on this side compared to this side. So it's going to want to flow from here to here. Okay, so it's going to go from right to left. So how does it get through there? It's going to radiate out. It's going to warm this glass fiber up. Then that's going to have to warm it up. And then it's going to radiate across. Maybe some convective heat transfer will occur. Eventually this will heat up. And then remember, that's going to radiate in all directions this way, including some of it back that way. That's very, very important. Some of it's going to radiate backwards, and then it's going to go back, right? So it actually traps some of the heat in there. And then it's going to radiate across here. It's going to radiate across there. Maybe it's a convective loop. Some of it's going to transfer up through convection here. Maybe it's going to radiate there, right? It's a mess in there. It's a maze. And so in order for heat to get from one side to the other, it has to go through all of those little barriers. And those barriers are all based on the air pockets. The material as well, but the air pockets are the essential aspect of this. If you would compress that, right, compress it, right, and get rid of all those air pockets, that heat's just gonna go right through it because there's no air pockets to slow it down. Okay, so that's really, really important. And the same thing with foam, right? This is the electron microscopic view of foam. And again, it's all about the air gaps. And this is especially good because there's no way for it to flow through there. It has to warm it up. Like this looks like there's some gaps so you can kind of get around things, but this is closed cell foam, and so it's really, really difficult to get through. Okay, so it's all about the air pockets. And if you look again, the U value is resistance or transmittance, and the R value is resistance. They are the inverse of each other, right? So U is 1 over R, and R is 1 over U. Okay. Remember, you can add R values, you cannot add U values, just as a sample of how to what not to do. So if I have these following layers and I add them up, so I have R1, R2.5, and R3.5. I add them up, then we get an R7. Okay. So what happens if I convert these to U values and add them up, just to show you why you can't add U values. So let's convert these to U values and add them up. So we get 1 over 1, which is 1, 1 over 2.5, which is 0.4, and 1 over 3.5, which is 0.286. So we add all those up, we get a 1.69. So that's what we get, 1.69. So that's wrong, and I'll show you, because the right way to do it is to add up all your R's, okay, and you end up with this R, and then you invert that, and it's 0.143. Okay, so that's actually the U value of those surfaces. You stack them on top of each other, and you have R7, which is a U of 0.143. But if you do it this way and add the U's, you're way off. You're way off, right? Okay, so that's super important. And also R values, sometimes you'll see building materials expressed as R value per inch, right? And so if you have something that say R 3.5 per inch, like most fiberglass bat and cellulose and stuff, if you have 3 inches of R 3.5, you just multiply the two together and you get R 10.5, okay? So that may pop up, but 14. Okay, so another core principle, or a set of core principles, is that we've gone over some of this before, that heat flow will increase, all else being equal, with increased surface area, with increased delta T, with increased U, and then increased time. So remember, our U factor is the BTUs per hour per degree Fahrenheit um, per square foot, right? And so more square feet, remember, means more heat loss. More a bigger delta T means more heat loss. And more time is going to mean more heat loss. We'll go over the increased U. I mean, that's obvious though. If remember, U is the measure of resistance, excuse me, transmittance. So higher U means more transmittance, more heat loss. Okay. All right. So there's actually a way to calculate the heat loss. We'll go over this in more detail later, but I want to introduce this now. And there's an extra credit quiz based on this. So our U value, okay, if we if we have one, if we have wood, which has a U value of about 1, what would the heat flow be in the following situation? So remember, uh, the U value is how much heat flows through a 1 square foot slab of material each hour when there's a 1 degree temperature difference. So if I have a U value of 1 and it's 1 square foot, 1 degree Fahrenheit in 1 hour, if you think about it, that should be 1 BTU of heat loss, right? Because it's how many BTUs travel through 1 square foot with 1 degree temperature difference for 1 hour, right? So that's going to be 1 BTU because it has a U of 1. What if we have the same thing, a U of 1, everything else is the same, but we increase to 100 square feet? So you may guess, you do the math, it's going to be 100 times bigger, or 100 times BTUs. All right, so now we have 100 times more. What if we take that same 100 square feet, remember we're a U factor of 1, now we increase the delta T to 10 degrees Fahrenheit for 1 hour, all right? So we've basically taken this and made it for 10 degrees instead of 1 degree. So you can do the math, or you probably can do this in your head. It's going to be 1,000 BTUs, right? Now, what if I take the same surface and I have 100 square feet at 10 degrees Fahrenheit for 10 hours? You can probably guess it's going to be 10 times bigger. The reason I show you this is just to show you that it's proportional, right? If you double the area, all else being equal, you're going to double the heat loss. You double the delta, it's going to double the heat loss. You multiply times a factor of 10, it's going to increase the heat loss by a factor of 10. All right. And so again, in general, heat transmission increases with increased U, increased area, increased delta T, and increased time. Sorry, that's not on increased time as well. So there's actually a formula for this when we want to calculate heat loss. So if we want to calculate the heat loss through a surface in BTUs per hour, this is our formula. So Q is your heat load or heat loss. It's UA delta T. So you want to jot that down. UA delta T. Q equals UA delta T. So the heat loss in BTUs per hour is U factor times area in square feet times the difference in temperature in Fahrenheit. Okay, pretty straightforward formula, and you can see it's all proportional, right? So this is our heat loss. If we double this, it's going to double that. If we double this, it's going to double that. If you double this, it's going to double, right? And so on. So it's all proportional. Well, let's do a couple of sample problems. So the previous surface, right? Remember it was a U of 0.143. What's my heat loss if I have 100 square feet of that surface with a delta T of 10? All right, so super simple equation. Remember, just U times A times delta T. So we have the U, we have the area in square feet, and we have the delta T. Just multiply them together, we get 143 BTUs per hour. That's it. So what if the delta T is 20? Again, do the math. It's going to double it, 286. What if we have a delta of 20 and it's 200 square feet? It's going to double it again, 572 BTUs per hour. What if its delta is 20, it's 200 square feet, and the U value is double? It's going to double again, right? So again, it's all proportional. This is a straightforward equation. Heat loss is UA delta T, and it's heat loss through a surface, used all the time in building calculations. Like if you're sizing an HVAC system, if you're sizing other things, you're going to use this all the time, right? So again, heat transmission increases with increased U, increased area, and increased delta T. Okay. And so remember that heat loss is driven by temperature differences. Temperature differences. No delta, no heat movement. Okay. And so if we look at the total heat, and this comes in handy in some of these equations, but I just want to introduce this concept now of heating degree days. You don't need to write all this down. For now, all you need to know is that a heating degree day is an indication of the average outdoor temperature relative to a comfortable indoor temperature. We'll go over this in more detail later. What you need to know is that heating degree days indicate a colder climate. Heating degree days indicate a colder climate. So this is a map of the United States, 2012, but this is pretty same, except everything's probably shifting northward because of climate change. But you can see in Florida, we have about 1,000 heating degree days. Sounds like a lot. Well, northern Minnesota, northern North Dakota, we have 10 to 11,000, right? So 10 to 11,000 more. What does that mean? Basically, that means if you build a house here and here, you're going to need about 10,000 times the heating up here than down here. Now, the cooling obviously will be a lot higher down here than here. So there's something called cooling degree days, but we won't deal a lot with that. But that's what a heating degree day is. You've probably heard that term before, but that's what it means. It refers to the general climate in the air. And more heating degree days mean you need more heating. Okay, so that's our building envelope, thermal boundary and heat transmission lesson. So by now you should know what a building envelope is, what conditioned space is versus unconditioned space, how heat is transmitted through a surface. Remember, it's all about the pockets of insulation. Has a high R value and a low U value, and that helps prevent heat transfer. And then you have the basic heat loss equation, UA delta T. You know that heat transmission increases with increased delta, increased time, increased area, and decreased U. That's really, really important to understand that concept. And then we also went over the basics of what a heating degree day is. And that's it for this lesson.